welcome. Thank you all for showing up to my talk. I'm really excited to share research that I worked on over the past year in Germany. This was me as the primary author and researcher on this, but I was guided by Ellie Pavlik and Alexander Koller. Ellie Pavlik is a researcher and professor at Brown University. I studied with her during my undergrad, and Alexander Koller is the professor who was hosting me in Saarbrücken, Germany during the past 10 months or so when I was doing this research. So the paper is called A Knapsack by Any Other Name, Presentation Impacts LLM Performance on NP-hard Problems, and I'll try to explain what all that means over the course of the next 30 to 40 minutes. Feel free to jump in with questions at any point in time. There will be some parts that will be probably easier to understand if you have like a formal CS background. I will try to give at least sort of a surface explanation of most things. If you want to get a deeper explanation, feel free to ask a question about it, and I'm happy to give a little more detail then and perhaps go into much further detail after the talk when we have more time. All right, let's get into it. So, sweet, we can move, awesome. So the overall structure of the presentation will be starting with the motivation for what the research was about and what was the main motivating question. Then I'll talk about the EHOP dataset, which was sort of the meat and potatoes of the research, this dataset that we designed to test our research question. Then I'll talk about the experiment design we created around that dataset, talk about the results we got from it, and I'll close with some conclusions and potential future work that I could have done had I had more time. So let's start with the motivation. Fundamentally, we want LLMs to solve problems, but we want them to solve problems robustly. Specifically, that means reasoning, not reciting. And this gets to a somewhat philosophical question about LLMs, whether they're learning representations during their training that gives them sort of first principles understanding of various logical properties of various entities, and they can actually think about this in a deep way, or are they more so reciting from training data, basically copy and paste, but with some adjustments being made according to the prompt and trying to basically fit it to what they're seeing. There's been some research in the past that was looking at this. So for example, there was this paper, Reasoning or Reciting, that looked at GPT-4's performance on a variety of tasks, including arithmetic and code execution in sort of default scenarios and counterfactual scenarios. So for example, we have arithmetic adding two-digit numbers together. The default scenario is we assume that these are in base 10. But if you understand how addition works and you understand how base 10 works, or just like how number bases work in terms of representing numbers, then asking to do it in base 10 might be a little trickier, but should not be impossible. Here we see a significant drop in performance when it comes to arithmetic in the default versus counterfactual. Same thing happens here in Python when you have indexing, as is done in Python and many other programming languages, as being zero-based indexing. And then if you ask it to do the same code but pretend for a moment that Python uses one-based indexing, again, you see the orange bar here is shorter. It's doing worse. Another example of this was people looked at the planning abilities of language models. This is where they get some sort of environment that they can interact with using certain commands, and they try to figure out a plan to achieve some sort of target, some sort of goal state that you outline for it. And so when they obfuscated these action names, for example, pickup becomes attack and unstack becomes feast, when you do that, they find that this simple obfuscation leads to a catastrophic drop in performance. And so the idea is that the functionality, like the basic logical building blocks that are in these planning tasks stay the exact same, but if you just use different tokens, so you eliminate the possibility that it was in training data, it becomes, again, we've got this catastrophic drop in performance. So that's sort of what I mean by reasoning versus reciting. This sort of indicates some reciting where as soon as you go out of context, complete catastrophic drop in performance. There are other cases in which it's less catastrophic, and so people still debate whether or not language models are performing reasoning, depending on how you define reasoning in aggressive air quotes for those on Zoom, just to make sure I want to make that clear. There's questions about how we define that. But we want LLMs to solve problems robustly. We want them to be reasoning in some way that goes beyond just simple recitation. And beyond that, we also want them to solve hard problems robustly. This is critical because if LLMs can only solve easy problems for us, that's not that helpful. We can solve easy problems ourselves. If I'm trying to figure out what 3 times 11 is, I can do that mental math faster than it takes to pop open a ChatGPT tab, ask the question, get the tokens to stream back, read the answer, make sure I understand it and think that it's correct, and then use that. So we actually want them to solve hard problems for us. And the question is, can they actually solve those hard problems robustly? Because that's when it actually really matters. There, if you do something where it's out of context and all of a sudden performance goes away, now it's not really going to solve your hard problems for you. And that's kind of the promise or the goal of LLMs in a major way. So this all leads us to the motivating question, can LLMs actually solve hard problems robustly? And this was motivating the research overall. I'm about to move on to the next section, but I want to stop and ask for questions if anyone has them at this point in time.
Yeah, I have a question.
Yes.
What are some of the instances that you mentioned on the last slide where it doesn't perform as poorly or as well?
That's a good question. So I guess it really depends on how you define being in context and out of context. That's sort of a fundamental question here. Is like, is this in distribution? Is this in the training data? A lot of the time, this is really hard to do because at least for proprietary models where we don't know the training data or we don't know the architecture of the model, it's hard to tell what would be something that we would say, oh, it's kind of cheating or like it's already seen this in training. There have been people looking at like whether language models can generalize to do arithmetic, just in general. Like the fact that it can do arithmetic with two-digit numbers and hasn't necessarily seen every possible two-digit sum example before, that's an indication that it is generalizing to some extent, right? Like I'm not saying at all that language models don't generalize. If they didn't generalize, there'd be no point to it. You would just memorize the entire thing or have a table of input, output, lookup. But the point is that language models are generalizing a little bit. Deep learning works to some extent, as we've realized, and this is driving a lot of what we're doing these days with AI. But then the question is sort of, when we get to these things where it seems like reasoning is required, how far can we really push that? Or how far does it generalize? And in a lot of cases, I guess the reasoning versus reciting question or the sort of out of context generalization does go to this question of how much are language models behaving the way we would expect humans who have linguistic capabilities to be performing. Again, we see like a lot of differences in the sort of general profile of performance and behavior in language models versus humans, right? It's very easy to personify them when we interact on a chat. But the question is like, where does that behavior break down? And where is it something where you would expect that because it can do X, it should also be able to do X prime or it should be able to do Y that's very similar? Where do those break and where do they stick around? So yeah, I think in general people keep using all the stuff that they generalize well. Like they can do poems, they can write new poems that they've never seen before, that no one has ever seen before. You've seen the ChatGPT limericks that were happening even with like earlier versions. So that's an example of something where it's out of context. It's never been asked to do that before. It's never seen that before. It's seen similar things that were similar enough in training data that it then generalizes. But then again, that's that question of defining, is that in context or out of context? I would go so far as to say that that's sufficiently out of context that I would count that as reasoning or generalization beyond that. But then when we get to sort of mathematical reasoning, that's a different domain. Any other thoughts at the moment? Again, feel free to pause me at any time, but I just wanted, every time I come back to this.
How do you control for the data set?
What do you mean, how do you control the data set?
Well, how do you control for it, like as the inherent question you're working on?
Sure. So that's a great question. How do we create a data set that tests these questions of like whether they're generalizing without being able to know what they trained on?
Yeah.
The only answer I've been able to come up with so far, and I've done actually 2 different research projects, one of them being this one that worked on this sort of question of generalizing and the reasoning capabilities of language models. The way that we've been doing it is you create a novel data set. You create novel questions that you're very confident would not have shown up in the past because you've created them from scratch and they don't look like something you think would have been on Wikipedia or Reddit or anything else that might have been scraped in the process of constructing the data sets for these models. Of course, that means that all of this stuff has, like, these data sets are not evergreen. The next time people create a language model, if this stuff is publicly available, which my code base is, then there's a good chance that GPT-6 or whatever will be able to see all my stuff, and then this data set no longer tests for whether or not it's generalizing beyond training data because it's possible that there's been this leak. But the idea is that with certain language models that were released before this data set was created, you can be confident that it didn't see something that was super similar to this, at least in the ways that we expect. And I'll describe some things in this section in a moment that will hopefully elucidate that more. Cool. All right, time to get into the big section of talking about the EHOP data set. So EHOP is everyday hard optimization problems. And so the idea is we wanted to get these hard optimization problems and talk about them in everyday nature, trying to see whether we can do this robust reasoning in contexts that language models haven't seen before. To start off with, how do we make sure that these are hard problems? I'm going to talk a little bit now about complexity classes. First of all, there's the class of NP problems. These are problems that can have a yes or no answer, and that if you give a yes answer with a solution for why it's a yes answer, it's pretty easy. That means in polynomial time, you can check that you're correct. An example of an NP problem is the traveling salesman problem. We've got a bunch of nodes connected to each other. They've got different distances between different nodes. And then the question is, can you visit all of the nodes and come back to where you started without going over some amount of distance? So for example, here, I can ask you all, can we do it in 15 or less? If we say like each of these things is a mile, like the units are miles, can I start at one of the nodes, visit all the other nodes, and come back in 15 miles or less? Yes, it's a full loop.
I think so, yeah.
This is
I mean,
something.
there's 10 lines, right?
If you go as a star,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah. So like 1, 2, 3.
So if you go in a circle, if you go on the outside, for example, right, that would be 1 plus 7 is 8, plus 6 is 14, plus 2 is 16, plus 7 is 23.
Never mind. No, you can't.
So that would be 23, so that would be too much. So we're trying to get 15.
Oh, you're saying you have to visit all of them?
You have to visit all of them.
Oh, 1, 3, 2.
Isn't this the problem where you shouldn't really go over the same graph twice?
Well, I mean, ideally, right?
Go over the same
Is
route.
that
You should never, you'll never be able to reuse an edge in this.
Oh, you're saying as like you can't, right? Like if you can, you still shouldn't, but it's an option. So you're saying
You can't. That's a constraint. I guess in some cases there may be a thing where like going backwards actually helps, but unless we assume that you don't go backwards. This is open to people on Zoom. You found 15? What's 15?
Can I draw it?
Sure. Or you can just like trace it out.
Yeah, you go here, 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 like that.
Like that?
Yeah.
There we go. Awesome. So that's 15. Using all of the smallest edges possible. And now that Keegan showed it to us, you can very easily look at this and be like, yes, you hit all 5 nodes in order, you come back to where you started, and it's 15. So that means it's easy to check. That makes traveling salesman an NP problem. Now, NP complete problems are the hardest within this class of NP problems. You figure out whether a problem is harder than another by whether or not you can simplify one problem into another in polynomial time. For example, there's the Hamiltonian circuit problem where you have a graph where not everything is connected and you want to do a similar thing of starting at one node, visiting everything else without repeating edges, and coming back to where you started. Now the question is like, is it possible here? Yes, but we would figure this out, we can figure this out using the traveling salesman problem. If we translate this graph into a new graph where every edge that existed gets a weight of 1 and every edge that doesn't exist gets a weight of 2, and then we say, can we do this in distance 5 or less? If the answer is yes, then the solution you give has to only use the edges that existed beforehand, right? If you go up and use one of the non-existing edges, you're going to push your distance too far and you're going to go over the limit. So if you can find the solution here, we can then translate that back to the original problem, and now this thing at the bottom right is a solution for the thing on the upper left.
And it's 2 because 2 represents the fact that you actually have to traverse 2 different times to get to that node.
2 is just because it's bigger than 1. And that just means that if you ever use one of these, it's going to be detected in your final distance by being more than 1 times the number of nodes, if that makes sense. Right? If you pick any solution that includes a red edge, you can't possibly do this in 5 or less. Does that make sense? Because like the minimum you'll ever get to use is 1. If you ever go above that minimum, you're going to go above the threshold that we're currently trying to hit, and that means you used an edge that didn't exist originally. And the idea is that translating from the upper left here to the second graph here is very easy to do. You can do that in polynomial time, no biggie. And this basically shows that the traveling salesman is harder than Hamiltonian circuit. If you can do the traveling salesman, the Hamiltonian circuit is not a problem for you. So traveling salesman beats Hamiltonian circuit. There's a few different proofs that get you to what are the hardest problems in here, but this actually ends up showing the traveling salesman is one of the hardest and therefore an NP complete problem.
It's not that hard.
Yeah, it's not that hard. It does get quite hard, but NP hard problems are at least as hard as NP complete problems, but now we're no longer constrained to the question of they have to be yes or no questions. You can now make them an optimization problem where you're just trying to go down or go up on some specific metric and see if you can do that. So NP hard problems. This will be our way of getting hard problems. Some of the advantages of using these problems in our data set are, first of all, we've got base difficulty. As Sasha said, they're not that hard, but they are kind of difficult. So reasoning is required. At least a little bit of reasoning. It's pretty unambiguous that if a language model can solve one of these problems, It's doing something we would call at least imitating reasoning, if not actually reasoning. There's this fast complexity scaling, which means that if you add a single node to the traveling salesman graph, you now get factorial growth in terms of how many possibilities you have to look at. In terms of efficient algorithms that would look at this, you also still can't beat that. You can't get back down to a polynomial time algorithm as far as we know. There's still a question of does P equal NP, and that's a separate thing, but that's the idea there. And again, since difficulty scales faster than prompt length, that means we can have prompts that are similar in length, but are very dissimilar in difficulty in terms of how much difficulty we're giving to the language model. So we can do a little bit of limit testing to see where they break down. Finally, these are common in everyday life. As Victor and I both know, we have helped route traveling salespeople from different job sites. And that's a difficult problem, and it does show up in real life. So this is a valid use case. Like, this does happen in real life. But yeah, so the three problems we ended up using are graph coloring. That's here in the upper left, where you have a graph, nodes connected with edges, and you're trying to color them with as few colors as possible. But you can't color two nodes that are connected to each other with the same color. So if they're connected, they can't have the same color, and that ends up constraining it, so you can't just use one color the entire time. You have to mix it up a little bit. We also used the knapsack problem, which you might be familiar with if you've done some leak code, where you have a knapsack with some capacity, and then you have a bunch of items with values and weights, and you want to maximize the total value in the knapsack without going over the weight limit. So here, the three that are highlighted in green get you your optimal solution. And I might just point out here that the item here that is highest value density, that is most value per weight, is the apple, and it's actually the one that we end up excluding to get the optimal solution here. So this is just sort of a thing to just give you an intuition about how these aren't obvious solutions. It's not like you just pick the most valuable stuff and you're done. Sometimes it turns out you have to switch things up a little bit. And finally, there's a traveling salesman problem, which we've already talked about, so hopefully that's clear. All right, I want to talk a little bit more about the graph coloring problem now, and I'm going to use that as a running example to explain the data set and how we constructed it moving forward. So one more time, graphic coloring problem. We've got graphs. Here are a few different examples. You've got nodes connected with edges. You want to use as few colors as possible to color all the nodes, but also if two nodes are connected, they can't share the same color. So in the upper left, when everything is connected to everything else, you can't ever use the same color twice, so you end up using as many colors as there are nodes. But in other sections, you can reduce the number of colors because there are certain nodes that are not connected. Any questions about the graph coloring problem or like how that works or anything I've said so far?
Can you recap that? I'm sorry, I got distracted.
No worries, yeah. So with graph coloring, we have graphs with nodes connected with edges. We want to color the nodes of the graph with as few colors as possible. That's the optimization metric. We're trying to minimize the number of colors. But two nodes that are connected to one another cannot have the same color. So that's why the red and blue here could not both be red. They're connected, so that's not allowed. You don't get to control the connections. The connections are given to you here.
Okay, so
Like you're just given a graph with the black edges connecting, and then the colors are the solution here. You're coloring the graph by coloring the nodes and trying to use as few colors as possible. In the bottom right, we have this disconnected node. It can be any color. And if we sort of say red is like the first color we use, if we're by default, we can use that color. There's no problem because it's not connected to anything else. So as Keegan correctly pointed out, if you use different colors for every single node, that will always be a valid solution. But the point is that we're trying to optimize the metric, as you said, of trying to use as few colors as possible. And that's sort of driving down that number when we try to solve this problem. This is related to the map coloring problem or the four-color theorem, if you've heard of that. That's based on this concept as well, or like it can be very easily mapped onto this idea. The four-color theorem basically tells you that if you have a graph that is planar, that is, you have a graph where none of the edges intersect with one another. So for example, this one in the bottom middle, that would break it because you've got this cross that you can't actually undo. Unless you move this red in here, then you would see that this is actually planar. So actually, I'm wrong about that. But it turns out that if you have something where you could move the nodes around without breaking any of the edges, like you keep all the edges the same, but you remove the intersections, like there's no intersecting edges, then you can use four colors or fewer in a graph coloring problem. So for example, this thing, I'm pretty sure K5, or the complete graph with 5 nodes, there's no way to move these nodes around so that stuff isn't intersecting somewhere. And that means that you need at least 5 colors. Oh, look at that, because you do have to use 5 colors here. So that math checks out, math is mathing. But for other things here, for example, here, right, there's no intersections anywhere, so we know that 4 is the biggest that we will ever need in a case like that. So that's the four-color theorem and how that relates there. Just for people online, I realized that I haven't been repeating questions, so maybe you guys haven't been hearing that context. Steph was asking whether the results of the research have basically been saying that language models can't solve problems robustly. To reiterate a little bit on what I was saying with Sasha, is that to some extent, they're able to reason robustly, or they're able to solve certain problems robustly or out of context. The question is, in some of these contexts where like the harder problems, can you still solve these things robustly? And so I would say that depending on sort of the difficulty of the problem or like the level at which you're testing, I think it's basically a question of what level you consider philosophically or theoretically to be sufficient justification to say these models are reasoning and they're reasoning robustly, right? Just producing more sentences that are grammatical that have never been produced in the history of mankind, that's out of context, right? Like if you generate a sentence that's never been generated before, sweet. And as all English speakers, we agree that's an English sentence. That is generalization. That's out of context, out of distribution, something like that. Or maybe not out of distribution, but it's something that wasn't necessarily in its context in the past. But then we might say that doesn't really count as reasoning. You just plugged one word instead of another, and otherwise the sentence is the same as something we've already seen. And so then you bump up the level again and say, well, if you can do two-digit arithmetic, that counts. And then language models kind of do that. And then if you make them huge the way like GPT 5.2 is, then sure, two-digit arithmetic, no problem. But then maybe 4- or 5-digit arithmetic, problem. I remember, I think just like a couple months ago, I was testing whatever ChatGPT was at that time, and I gave it like 8 2- or 3-digit numbers to sum up together, and it had like a 50-50 shot of giving me the right answer when I checked with a calculator. So there's still stuff there where it might not do it correctly. People will talk about how that's like limitations or like inherent limitations of the transformer architecture, and it may be that if someone can figure out a better way of doing this so that language models have more sort of symbolic structures within them, there may be a point where you hit sort of that singularity, and it will be able to do math at any level if you want. But I think the argument that I end up getting from this research, to cut to the chase, for both this and the previous project, the idea is a little bit more of language models are pretty good at languagey stuff in terms of like translating between different things and sort of I hesitate to call them soft skills, but like the ideas you might think about like with like writing well or like expressing thoughts in interesting ways. But then when it comes to doing sort of like hard math or like proof-based logic, that might be a point where it would be better to trust a symbolic system that you have hard-coded and a programmer has tested themselves, and then you use that. But the question, again, is like whether language models will scale up beyond that and like what gets changed. And you'll see a little bit more of that in the results in terms of how language models have been changing their performance on this benchmark depending on when and how you test.
Theoretically, the bar just keeps moving.
Right. And so the question is like, if the bar keeps moving, at a certain point, do we just say they're reasoning? Or do you say like fundamentally they're still doing copy-paste, still reciting even at the top level? Right? There's sort of philosophical questions to be asked here about like whether you talk about this behaviorally and you say, if it looks like a duck and quacks like a duck, like if it looks like it's reasoning and it sounds like it's reasoning, do we just say that it is? Turing tests, all of that, this sort of comes into all these questions of how we think about whether they're thinking or not with aggressive scale codes. Yeah, and then the question is, can you prove it? And I'm not sure if I can or you can. But any questions on the graph coloring problem, though? I think we're good. All right. So this was, one of the hard problems. Now the question is, we're talking about robustly. So we're going to try to take the problem and we're going to try to take it out of context or move it into different contexts that will test the LLM's ability to reason rather than recite. So we have the textbook description, the textbook version of the graph coloring problem, which we just described at length and talked about its connections to other graph theory problems like the 4-color map theorem. We also have costumed versions, what we call costumed versions, where we basically dress up the problem in a different context using different language about a different problem that just so happens to have the exact same logical constraints and objectives as the graph coloring problem. So for example, I can say, I'm going to host a Taekwondo tournament. I've got 5 participants. Here are the sparring matchups, and I want to assign them to warm-up rooms where they can stretch out and practice their moves. But I can't have competitors who are going to be competing against each other in the tournament to warm up in the same room. They might study each other's moves, they might try to get an unfair advantage somehow, so they need to be in separate rooms. But the gym is really restrictive, and I can't book as many rooms as I'd like, so I need to minimize the total number of rooms. Oh, look at that. You've got an objective of minimizing the total number of labels, which could be colors as well. And hopefully you guys can see the analogy here. It all maps on one-to-one, the exact logical constraints in terms of the constraints and the objective. But we've never said anything about graphs or coloring or anything like that. So the idea is like, can the model solve this problem if it's able to solve this one? Because if a human can solve a graph coloring problem, you'd expect that they'd be able to generalize to the Taekwondo tournament, for example. Another way we varied things was we had standard versions of problems, and then we also had inverted versions of problems. Here we took a little bit of what I was talking about earlier with the Hamiltonian circuit and traveling salesman problem being sort of equivalent, or like the traveling salesman problem being a thing that you could map the Hamiltonian circuit onto. Here we are able to map these two, the standard and the inverted versions, into each other, and I'll explain right now. In the standard version, again, I've already explained the rules, but in the inverted version, what we do is we still want to minimize the total number of colors, but the constraint gets flipped. So now if two nodes are not connected, if they're unconnected, now they can't have the same color. If they're connected, then it's fine. So basically reversing what constrains coloring. This is the question. It's like, okay, if we change those rules, then obviously that changes the answer if you're doing it on the same graph. But if we flip the graph by taking the complement, looking at all the edges that don't exist in the original, and using those as the new graph, then we've flipped both where the edges are and what the edges mean for the problem. And so if we flip both things, now the same coloring works for both. If you can solve the standard problem, you can solve the inverted one, and vice versa. So we use this as sort of a convincer that like these are equivalently difficult problems. If you can solve one, you should be able to solve the other, because it's really sort of a trivial thing. And really this is actually just sort of an arbitrary choice that we made in graph coloring, that we said edges represent the constraint that you can't have the same color rather than the absence of edges. Because really this is a binary label of whether or not these two nodes are connected. And so we're just saying, instead of looking at the zeros, we're looking at the ones, or vice versa. Then if we costume it, there we go. Now we can do this version, which is what I called the student groups costume, where you say, I'm a teacher, I want to assign my 4 students to different groups, I need the groups to focus, so I need to make sure that no 2 students who are friends with one another are in the same group. See where this is going? They're going to be assigned to groups, we have edge constraints. It's the same thing. This is actually being done for the exact same graph, so you can see, come on. Yeah. Same numbers of like 1 and 3, 1 and 4, 2 and 3, 2 and 4. Those are being kept all the same, and we're still providing the same constraints and the optimization of trying to minimize the total number of groups, also known as colors. But of course, we're not using that language here. And so if you can solve this one, we expect that you should be able to solve this one too, and vice versa.
Was there any consideration behind the fact that now that you add this additional 2 sentences, and I know that's a small fraction, that increases the context window that you're actually sort of doing something? It's like an inherent, I know it's not an inherently different problem, but was there any sort of consideration?
Yes. So for those online, Victor's asking about prompt length, and isn't that a consideration? Because if you make the prompt longer, that could be an issue. That could be an issue that might affect our research ever so slightly. In general, right, this is for the smallest problems that we use in terms of like a 4-node graph, but the function for the length of these prompts is a linear function, right? We have some constant amount of text on either side of the stuff in the middle, and then the stuff in the middle grows linearly with the amount of information you need to present. And so this thing actually grows, so as you make the problems larger and larger, you actually end up getting prompts that are pretty comparable in size. And that being said, between these two, there isn't a ton of extra text. There are some more tokens. There is some variation here, to be sure. And if I had to do it all over again, I would definitely have counted tokens a bit more carefully and tried to make it closer. So that could be a small confound, but I would say that for the most part, if that extra amount is in fact what's causing it, I would at the same time also argue that it does get looped in a little bit to whether it's reasoning or reciting. If the brittleness is so severe that you add 2 sentences and the thing breaks, even though those sentences are relevant or like part of the context, and now you have to do a teeny bit more digging for the needle in the haystack, I would also say that could be considered an issue as well. But yes, but totally valid concern. We had to think about that. Reviewers asked us about that, and we tried to cover it with some calculations for that. Steph, was there a question? Right, so Steph is asking about whether specific contexts might be the ones that break it, or maybe specific contexts actually work. That's a question. We tested a few different costumes for each version and sort of used that sort of to average out and aggregate across those. There's definitely variation in performance, and so certain contexts work better than others. In general, I did my best when writing these prompts to make them as clear as possible about these are the constraints, these are the objectives, and if you sort of look at those rules, you should still follow them, even if perhaps there's some sort of real world scenario or some real world context that might affect your thinking a little bit. I did my best to like give it an explicit constraint here, like I want to minimize the total number of groups. Maybe a school teacher doesn't necessarily want to minimize the total number of groups, but I've said it explicitly here, and like this is the task I'm asking for. And so while the person may say, oh, actually, if you use a Kahoot, you don't have to use any groups at all. because now we're in the student-teacher context and we don't actually need to think about it. But given that I'm being very explicit here and here about everything that I want and how I want it, it's one of those things where we hope that that controls enough of it to make that happen. But totally, different contexts might be more distracting than others. And so we tried to sort of account for that by using a couple to sort of average out those effects. So Armand's asking me about whether they're specific to specific problems. So it's the graph coloring, knapsack, and traveling salesman problem that I mentioned before. Those are the three sort of base problems that we use for standard and costumed, or like textbook and costumed, as well as standard and inverted versions. We did inversions for those two versions as well. In fact, if we look at the EHOP dataset by the numbers, we have those three domains, graph coloring, knapsack, and traveling salesman. We have 6 scales for them, or 6 different sizes of each problem. So for graph coloring and traveling salesman, both of which are graph-based problems, we scaled them from 4 nodes up to 9 nodes and everything in between. And for the knapsack problem, we used 4 items up to 24 items with even intervals of 4, 8, 12, 16, up to 24 to get 6 different sizes of problems there, of like how many things you'd have to compute with and look at. For each of those combinations, we generate 25 instances. Those are specific graphs or specific knapsack problems with numbers assigned to everything. And finally, or not finally, actually, we have 4 templates, 1 textbook and 3 costumes for each domain, and 2 variants, standard and inverted. And if you do some quick math, that comes up to 3,600 natural language tasks in total. Additionally, we also looked at how greedy strategies perform on these problems. If you're familiar with computer science, you'll probably already know that greedy strategies are straightforward algorithms that iteratively build a solution. They don't allow backtracking, so if you realize later on, oh, I shouldn't have done that, it would have been better to do something else, it's too late. Greedy just keeps moving and accumulating more. And it'll give you a valid solution, at least in most ways that greedy algorithms are applied, but they're generally suboptimal. They're generally not going to give you the optimal solution every single time. But sometimes they'll luck into the optimal solution, because greedy strategies will at least give you something that has a decent chance of being optimal. When the problem gets huge, it's less and less likely. If there's like a huge solution space, they're less likely to get you the right answer. But we can use this actually to filter out some of the problems that we had in the original data set. If you have problems that could be solved optimally by a greedy strategy, that might indicate that they're pretty easy, or like they're an easy version of the problem. And so we actually created a hard version of the data set as well as a random version. So the random version, we just generated all of these instances completely at random and just saved them. And then for the hard version, we generated again, but this time whenever we generated a problem that was solved optimally by a greedy strategy, we chucked it out and generated a new one. All of that gives us instead 6,800. It doesn't double exactly, and it's almost 2 data sets, because graph coloring, if you have 4 nodes or 5 nodes, it's very difficult to actually construct a problem there where you're not going to solve it optimally with a greedy strategy, because those are pretty easy, at least for a greedy strategy, to do. So we eliminated those 2 scales for the hard data set. But otherwise, we kept everything else, and that's why you get the discount of 400 off on the big thing. What were we expecting to happen? So given the past literature of seeing that models seem to do worse in these counterfactuals or going out of context, out of distribution, we were expecting they would probably perform worse on costumed and inverted problems. We found, or I'm not going to say what we found just yet, but we would expect that if you go out of context or if you go out of distribution, do stuff that's less like the things you would see on Wikipedia or in a computer science textbook, the language model is going to get worse at solving those problems, because it will at least first need to take the step of figuring out, oh, this is the graph coloring problem, and then solve. I had done like a little bit of sort of empirical testing with ChatGPT, asking it a variety of problems. The point, at least once we started creating the data set, was to sort of like hands off and don't like test the data set before we're done, right? Because that sort of pollutes the whole scientific method in this case. But I would say like based on that, I was really uncertain. And I guess that's kind of the point of the research, is to like find out the answer, because while the answer may seem obvious in retrospect, at least going into it, I was genuinely unsure of like whether all of the problems would be solved across the board, or whether like even the best models we tested would solve like one problem by accident on occasion and everything else would just be zeros. And then we would have to change the difficulties of the problems and do all of that. But yeah, to be fair, we did sort of like pick these scales a little bit depending. We picked these scales using greedy algorithms to see like where greedy algorithm performance just fully dropped off. And so with like the traveling salesman problem, for instance, if you go up to 10 nodes, right, that's 10 factorial possible routes that you could look at, only 2 of which are correct, right, going in one circle or going in the opposite direction. There's only 2 possibilities out of 10 factorial. I don't know what that number is, but it's ginormous. And so chances of a greedy algorithm sort of stumbling into that get pretty darn low. And so we said like, okay, at that point, we don't expect the language model even to do it. And we did test language models, at least on like graph coloring problems with like 12 or 15 nodes. And at those points, it does sort of just drop off a cliff. But yeah, in terms of like actual expectations for precise numbers, I didn't really have anything. And it was one of those questions of like, will we be right? Will like some of this stuff actually turn out this way or not? And we'll get into that in a moment once I cover experiments and then talk about results. But yeah, the data set was really the big chunk of the presentation, or sort of like for me, the thing that I get excited about, because I spent months of my life researching the literature and figuring out how to make problems equivalent to each other when I invert them and all of that, which was a lot of fun. And yeah, in terms of experiment design and results, they kind of wrote themselves in terms of how those came out. Cool. Let's talk about experiment design. Models. Everyone loves models. So in terms of the LLMs that we tested, we used a few that were sort of standard non-reasoning models. This is sort of at the time that reasoning models started becoming a thing. But we had GPT-4o, specifically the 2024 August 6th edition, if you want to be precise. We also had the Llama 3.170 billion instruct model and Qwen 3 32 billion in the non-thinking mode. With Qwen 3 32b, you can toggle whether or not it's going to produce thinking traces, and so we use it both in the non-thinking version as well as in the thinking version here as a reasoning model, in addition to DeepSeek R1, which came out kind of shortly after the first version of this paper and the first version of testing this data set. With the models, we used a variety of different prompting strategies. We used one-shot, that's providing one example input and output of the exact same variant and template. So if we were talking about student groups, we would have given a student group example and a student group solution, and then given a new student group problem and asked it to solve it. We also use zero-shot chain of thought, which is you just say, let's think step by step at the end. We only do that for the non-reasoning models, because anyone who's done chain of thought with reasoning models knows there's no need to do that. They've been reinforced enough, and they will just become philosophers if you ask them to think extra beyond what they've already been trained to do. There's also one-shot chain of thought where we give an example of a problem and solution before the thing we actually ask. But in this case, we give a chain of thought reasoning for the solution that we provide. And finally, we have a neurosymbolic approach using integer linear programming that used two different languages. There was this LP specification language, a linear programming specification language, and Python. Integer linear programming is another NP-hard problem, but it's one that's fairly abstract, where all you do is you give it some objective, some metric that you're going to either maximize or minimize. And this is going to be a linear combination, if you remember stuff from linear algebra, where you just have coefficients and variables. So you say 5x plus 3y minus 2z. I want to maximize that total combination. And then you say, by the way, x plus y has to be less than or equal to 2. And z can't be 0. And you give a few constraints like that. And this happens a lot in operations research, where people have a bunch of things of like, we have to constrain all these different things and we're trying to optimize this metric. How can we do that? Integer linear programming is in some ways sort of this generic language that could work for all kinds of problems, including the three that we've given: graph coloring, knapsack, and traveling salesman. So the way that we use integer linear programming as a prompting strategy is we would have, actually before we get to the code example, I'll just explain. We would give the problem to the language model and we'd say, please translate this text problem into code that would solve this problem. We would then take the code from the language model, run it on our own system, and give the output back to the language model, assuming that the code ran successfully. And then we would say, okay, your code outputted this. Please translate this back into natural language and give me the output that I asked for at the very beginning, because I don't know how you wrote your code. Maybe you reversed the order of the list, so I want to make sure you give me the right order and all of that. In terms of LP and Python, these are what they look like for the same knapsack problem instance. To give a little more context, ta-da, color coding, just to see what sort of corresponds across here, right? If we have maximize here on the left, that's what grb.maximize is doing. We used GurobiPy as a specific package if you guys are interested. For those of you familiar with Minizinc, similar idea here as LP, where you have, again, like I said, 4x1 plus 3x2 plus 9x3, etc. Where here these are binary variables indicating yes or no whether or not this item was put in the knapsack. And the constraint is saying, by the way, the weights of these items gated on whether or not they're in the knapsack can't go over the capacity of 33. They have to be less than or equal to it. That's what's happening on the left here on the Python, in the LP, and then Python does a similar thing where you return a model that once it's optimized will have solutions in it if solutions exist, and if so, it will give you the best possible answers. Okay, when we got a result from the language model, we could classify this as either invalid or valid. An invalid result would mean that's either incompatible or erroneous. Incompatible meaning this doesn't look like a solution to the problem. I asked you to give me colors for 5 nodes in a graph. You gave me colors for 10. I don't know what to do with that. Or you gave me a recipe for pie. That again, not compatible with what we were asking for. Erroneous is something that looks like a solution. I asked for 5 colors for 5 nodes. You gave me 5 colors for 5 nodes, but nodes that are connected have the same color. You broke the constraints, so that doesn't work. With valid, you can have suboptimal solutions where it totally works, but you use more colors than you needed to. As Keegan pointed out earlier, you could use 5 colors on a 5-node graph, but if it's not a complete graph, if not everything is connected, then you probably could have done some optimization that would have made it better. And finally, if you have an optimal solution, you use the fewest colors possible. You got the shortest distance in traveling salesman, or you got the most possible value in knapsack.
Before you go any
Yes.
further, what was your system prompt? Basically, like, I'm asking this because this LLMs are basically trained on human data, and humans, if you give them any kind of emotional change, oh, you did great, could you like solve this problem now? Or you're an assistant, you can take a break and then solve this problem. Your
Sure.
life depends on this problem, something like this. Did you go through those checks?
Right, so the question was about system prompts. We didn't provide a system prompt in this. I think one thing that I may have not mentioned so far is just this idea of like how much we want to hold the hand of the language model in terms of helping it solve the problem. And so the idea here, just to keep in mind, because this was the thing that I had to remind myself when I was working on this project, is that the goal is not to get language models to solve these problems. We have computer algorithms that can solve these problems. It's not a thing that we're trying to solve. The point is, can we find out this discrepancy between the standard and the costumed, or the textbook and the costumed, or the standard and the inverted problems? If we can, then that might indicate some level of recitation versus reasoning. In terms of system prompts, that would be another dimension that we could try to vary things on, but it was just one that we decided to leave alone because if you now have multiple different system prompts that we might be using, right? You remember it was 3,600 before, and then it went up to 6,800 for the 2 different data sets. If we just multiply that by 2, our API costs are going to go up by 2, and we're a university, not a startup, so we don't have Series A funding. We need to keep the token counts low. So in terms of system prompts, we didn't test those, but that would be another thing that could be future work, actually. That would be an interesting thing to look into. And we did consider it, but it was just another thing that was kind of out of scope. All of this is probabilistic to some extent, right? OpenAI's models all have like a little bit of a random seed, which you can set. And even though I found out from my peers that even if you set the random seed, you try to turn temperature down to 0, you do all these other things that are supposed to make the model deterministic, you still don't get deterministic output. And so even with that, with the system prompts, right, there's a possibility that you just happen to hit the right nodes. But again, this is like now the question of like, are we hand-holding or like doing, right, instead of stochastic gradient descent, I don't know if you've heard of it, but like the doctoral student gradient descent, where it's like, instead of gradient student descent is like the student doing grid search effectively by just trying out a bunch of stuff until they find the one thing that works. And the whole point is not to have us do the work, but to have the language model do at least some of the work and see whether it can do it. Whether saying your life depends on it actually changes performance. I don't know all the results that have come out of those things, but yeah, we decided not to incorporate that feature as yet another dimension. As I mentioned before, like that would just grow the things. Yes, for day-to-day. I've heard that Claude code gets better when you curse at it from people on the subway. Like I got on the subway a little while ago in Canal, and then they were like, oh yeah, curse at it and it works. So from engineers on the street, you heard it first. All right, so results. Let's look at the numbers. So this is for the EHOP random data set. So this is the randomly generated problems. It's a little bit blurry, but hopefully you guys can make it out. Right, we split it up by problem, so graph coloring, knapsack, and traveling salesman. Let me move zoom out of the way just a teeny bit. Hopefully that works for a little while, at least. Oops, I moved. Okay, so with here, there's a couple things to look at, right? On the x-axis, we have scale for each of these problems. As you see, when scale goes up, performance goes down. Whoop-de-doo, what a surprise. But it is good to make sure that language models are in fact behaving in this way that we'd expect, that they do worse as problems get harder, just objectively harder because there's more solutions to look at and more potential ways of solving things. Also, just to be clear, we have optimization accuracy here on the vertical axis. So this is what percentage of the results were in that final optimal category, not incompatible, erroneous, or suboptimal. Okay, cool. So with all of that being said, we also have looking at one-shot chain of thought versus ILP Python for specific stuff here. We did this because while we had other prompting strategies, one-shot chain of thought sort of was a representative version of quite a few of the other typical prompting strategies, and ILP Python was doing pretty well consistently across the board, whereas the LP was doing less consistently well, we think probably because it was out of distribution, or like LP code is not a thing that language models see nearly as much as Python code on the internet. So beyond that, one other observation, or two other observations to make is, right, with the chain of thought prompts, they sort of go down steeply or sort of, get to a relatively low performance by the end, whereas the ILP Python strategy, at least for the GPT model, is doing much better in terms of consistency or robustness across time. As you can see here with graph coloring, it doesn't start out very high, but the point is that it doesn't fall significantly lower than it started out. It sort of does a consistent performance. And in terms of knapsack and traveling salesman, this is the here where it sort of degrades, but it degrades fairly gracefully relative to the other models. And finally, we have greedy strategies here in black. You can see that graph coloring, greedy strategy is getting 100 for the first 4 scales, and then it drops down a teeny bit, but it's outperforming LLMs across the board. Yes, Dylan?
Is this your textbook problems, or does this include the entire data set?
Oh, good question. Yes, sorry, this is for textbook standard. This is not looking at costuming or inversion yet.
And then other question, so GPT Llama, both non-reasoning models.
Yes, both
With
non-reasoning.
chain of thought in the one-shot prompt, right? So you would put reasoning in the one-shot.
Yes.
Would you prompt for reasoning tokens in the output of the non-reasoning models, or would you just say, hey, just give me the answer?
For reasoning models, we did not give any chain of thought prompts or like ask it to reason extra, because even if you don't ask, it usually gives you too much. At least in my experience.
For the non-reasoning models, would you ask it for reasoning, like chain of thought output?
Yes, if we say one-shot chain of thought, we would say like do all of that, and I believe we would say let's think step by step. But perhaps I might be misremembering there. It may be just there that we assume that the example of showing reasoning is going to be enough to encourage it, although that could be wrong. I'd have to check. But yeah. As I was saying, greedy strategies outperform LLMs pretty much across the board, except for like a few exceptions here on the side. But it's just worth noting that like these algorithms that are pretty simple and not guaranteed to be optimal are still doing better than LLMs in some cases here. When we look at the hard data set, in general, performance just goes down as sort of expected, because we're now filtering out the problems that seemed easy to us. And in general, we get mostly similar trends. Again, GPT with the ILP Python strategy, this is the dashed blue line, is doing pretty well. It's degrading fairly gracefully across these problems. We see a little bit of a dip at the end of traveling salesman, but for the most part, right, it's doing pretty well, whereas when we do GPT with one-shot chain of thought, it just crashes after the first scale. And again, for 4 nodes, I think you're looking at 6 possibilities, 2 of which are correct. So chances of getting something correct there are pretty high. Like I said earlier, I didn't have like super specific expectations for how the numbers would look. In terms of this degradation happening at a certain point, that wasn't super surprising, because it seems like, again, this is factorial growth. So if you go up to 5, you've multiplied the total solution space by 5, or at least by 4, I think. And so, yeah, the fact that like at a certain point it just gets to this scale that is just too big was unsurprising. But yeah, the fact that it happened so soon and not at 6 or 7 was a little surprising to me, that like it didn't take very much to push it into a territory where it couldn't do it.
What is the weak there?
Yes, so remember we filtered out, so this is the hard problem, so we filtered out stuff that was solved optimally by a greedy strategy. We also used weaker greedy strategies that use like a slightly worse heuristic based on like other experiments we had done in terms of how often they solve things optimally. These were ones that solve things optimally less frequently, but since they're distinct greedy strategies, they might solve optimally the things that another one didn't. And so we provided one for graph coloring and knapsack as well. For traveling salesman, there's kind of one heuristic for greedy, which is just go to the next node that's as close as possible and just keep going until you get to, right, like go to the closest unvisited node and just keep doing that until you get back to where you started. And in terms of other heuristics, there really aren't any for greedy, for traveling salesman, which is why it doesn't have an actual line.
In terms of ILP, are you specifically asking it in the prompt to turn the question into a mathematical formulation?
Yeah, so sorry, I should have mentioned this a little bit more. With the ILP strategy, we would provide an example of code, not for this specific problem. We would just say like, this is what the formatting looks like. So we'd say like, here's an example of a linear combination of like 5x minus 3y plus 2z, not related to the problem at all, but we'd just be like, this is how it's formatted. Please reformat this text as code that looks like this or looks like this Python code, and make it so that when we solve this function in code, we'll get an answer to this problem.
And that's not considered one shot because it has nothing to do with the answer. Just sort of
Exactly.
more context.
It's more so formatting
It's
and
like ILP context, sort of.
Right, exactly. It's not considered an answer to the question because it hasn't seen an example of another question being answered with this code or anything like that. And again, the code is not related to the problem at hand. Okay, so again, this was textbook standard, as Dylan helpfully reminded me to point out. Now we can look at textbook versus inverted versus costumed. So this is graph coloring knapsack traveling salesman for eHop random on the non-reasoning models, GPT, Llama, and Quen in the non-thinking mode. So you can see across the board here, pretty much all red, right? Everything goes down relative to textbook, right? The numbers here are all relative to the textbook in their same category. You get a few points where they go up a teeny bit, but for the most part, you get significant downturn here. And it's also worth noting that the greedy strategies, again, across the board, if you sort of average them out, are doing better than even the textbook strategy for most cases, at least in graph coloring and knapsack. In traveling salesman, though, you get this one case of ILP Python GPT doing quite well at an average performance of 86% optimization accuracy versus the greedy getting only 30. As Sasha pointed out earlier, right, like stuff sort of falls off pretty steeply there, but this is the thing where we saw earlier that it stays pretty consistent up here, and so its average is closer to 86 or so. For the hard data set, there's a little bit more of a mix. In general, we saw that where you get some of the green stuff or where you get some of the increased performance for inverted or costume problems, it's more so on the points where you already had low performance. So for example, here we had one-shot Llama textbook graph coloring problem. You got 1% optimization accuracy versus inverted gets 4%. Here it feels like it's more so just like random numbers where you get a little bit of noise and that accidentally sort of boosts you a couple percentage points, but it's not one of these things where you're at like 67% and go up to 80. It's more like 3 versus 4 or 1 versus 4, and it looks like a significant change, but it may not be quite as significant. There's still this unanswered question for us, which is like, why is knapsack getting more of the green than the other two categories? I looked at this from practically every angle I could think of, and there's no clear answer, to me at least. I would love to have one of you guys take a look at the code base and run some diagnostics and let me know what I did wrong. But as far as I can tell, at least the general trend continues to be that it does worse for the inverted and costumed versions. Again, costumed here is the average of 3 costumes. So just keep in mind that this costumed row has 3 times as much data behind it than the textbook and inverted. I realize it's a little bit of a misleading table in that sense, but otherwise, hopefully that makes sense. Yeah. Any questions on Zoom, by the way? Hopefully, like you guys can still hear me when I'm talking in a different direction. Yeah, good, awesome. But yeah, if you have any questions, again, feel free to unmute or raise your hand. Hopefully I will see that or Sasha will see that and flag it. But yeah, okay. Finally, reasoning models. We have R1 and yes, we'll go back for a second. So the question is, why is the costume knapsack problem doing better in many cases than the textbook? I don't have a great answer to that. There's some hypotheses. Steph, you got a question or a thought? Sorry, okay. Like I mentioned before, right, a lot of these things are like this 2.2% over an 8.7, where it's already quite low, right? It's 8.7% of the time versus 10.9. It's like, okay, so these are like small potatoes or like small things where like perhaps you get these random deviations that make you go up. But there's also like random deviations here where you go down, like -7 or like -1 here. And so maybe it counts as much as the negatives do. In terms of why costumed specifically in knapsack might be working, there's a question of whether the math in knapsack is just one of these things that the model has seen sort of generally, and so therefore is better at generalizing regardless of the context, and whether or not it's a knapsack problem or presented as a knapsack problem or the other costumes we use there. This may be, right, these costumes are different for all 3 because I had to come up with different things that match the different logical constraints. I couldn't be student groups for like collecting students with values and weights. Like that just doesn't work, right? So we had to use different context for all of those. It may be that the contexts I used for knapsack here don't mask the knapsackness of the problem as well. And so maybe just more obvious to the model what's going on here, whereas these ones were harder for it to sort of puzzle out and figure out what's going on. There's all kinds of variables there that are hard to control for in terms of what might, again, link into training data, as I think you or Steph asked earlier, in terms of like, how do we know that it's out of context or like out of distribution? We don't. It may be that, in fact, the language model has seen some of the stuff that I put in here, although I was pretty confident what I was creating was fairly novel and different from what other people had done. Like I would search for some of the stuff on Google and like check for that sort of thing, and most of the time when I looked for it, it was like the top 10 results or so on Google did not look like what I was talking about, or like didn't link from the description that I gave of like trying to organize a party, but some of your friends have dated before and you want to therefore exclude some of them from certain parties, hence graph coloring. while that happens, right, like if you search for that, you're probably not going to get graph coloring as like your answer, or like, hey, use this greedy strategy for how to like plan your birthday. Like that's not going to be a thing, and hopefully won't be a thing that's been like associated within the language model across the board. Sure. So in terms of model performance, we saw that GPT was doing pretty solidly. If you want to, right, you can do some of the math here. It's a little bit annoying to do, but like 8 plus 11 gets us this 19, and this gives us 14 or so, right? So GPT is outperforming Llama, at least on this row right here.
It's just like 1 to 1. Yeah, that makes sense.
Right, I mean, if you, like I said, like the table is constructed in such a way as to sort of specifically highlight these differences between textbook, inverted, and costume, because that was what we were looking at in this analysis right here. In terms of looking at the models across what's going on, yeah, you can sort of see that like GPT is doing better than Llama and Quen. There are certain places where you might get a little bit of a surprise where like Quen is outperforming GPT in certain cases, but it's one of those things where, right, the whole point was to ask whether language models in general are reasoning robustly, and so that's why we're looking sort of within a column, how does Llama compare to itself when it's being shown two different things. And so it's one of these things of like, if we got like zeros or like very small numbers across the board in terms of differences for a specific model, that might indicate that it's at least somewhat more robust in some sense than another model where it has bigger swings depending on what it sees.
It's crazy to see how inverting like the graph coloring problem absolutely destroys all of
Yeah.
zeros in everything.
Yeah, there's a lot of things there where, and the thing was the inversion for graph coloring was quite subtle. We changed one word from connected nodes to unconnected nodes, which again, flips what's going on. I looked at some of the reasoning traces, at least for reasoning models, and for some of the ones where we did like one-shot chain of thought, for example. There, sometimes you see the model say like, that must have been a typo. Like, you couldn't possibly be asking for that because the graph coloring problem always works with connected nodes. And it's like, okay, so there's some overfitting there where like, if you give the inverted version of one of these problems, for example, with traveling salesman, we say maximize the total distance instead of minimizing it. It might just misinterpret it and say like, I actually want to do the standard version even though the person must have made a typo because it's disagreeing with what the standard thing is. We also looked into an analysis, and I don't remember the exact numbers, but you can look at the appendix of the paper if you'd like to learn more, where we looked at how often the solution given for the inverted problem is actually the correct solution if you were to interpret it as the textbook version, right? Like, is that the correct like standard coloring on the inverted graph, for example? And we found that actually in this case, like you get some of that for sure. There are places where it will color it correctly if it were using the standard rules instead of the rules that we actually gave it. But that's still not a significant enough percentage to like boost it all the way to being like the same performance or something like
Are these averaged on multiple runs?
These are not averaged on multiple runs, right? This is 25 instances. So each of these numbers represents 25 specific problems being given and then averaging performance on those. Right, again, costume is 75, or it's like triple that because it's the 3 different costumes averaged together. And yeah, we also wanted to try different seeds to see if like this is seed specific, like if you do seed 1, seed 2, seed 42, will the models do differently? I'd love to know, but again, it's just costly to rerun it over and over again. So that wasn't something we got to do. Another piece of future work of like if we had more time and money, then system prompts and seeds would definitely be a thing that I want to add into the mix to be able to check that sort of stuff. Okay. Yes, question. Yes. Right, so that's a good question. So knapsack, graph coloring, and traveling salesman are all very well documented problems because they're NP hard problems. Like I learned about this from a textbook. Like I learned about these 3 problems from textbooks and understood like computational complexity from a textbook. So there are Wikipedia pages devoted to all of these and how they're related to one another and how they're related to other problems. Knapsack shows up a lot in lead code problems. Graph coloring and traveling salesman maybe less so. But the question is like, right, is the fact that it shows up in lead code specifically, or like the fact that it shows up in some coding problem specifically, does that make it more likely that the model is better at doing it for that? Certainly, that would explain why it's doing so well when we do ILP here, like 92% versus like all of these low numbers. Boom, GPT knows how to code. Maybe GPT was trained on lead code and saw how to do this. Although then again, we're not asking it to do the lead code dynamic programming solution, we're asking it to do this ILP thing, which is less common, but still perhaps easier if you've seen coding solutions that talk about how to do knapsack more often than you've seen coding solutions for the other 2. But again, this is getting into like training data that we don't know about. There's certainly standard like versions of the knapsack problem explained on lead code. I've done them myself. Not that I can necessarily reproduce the entire dynamic program for you right now. This is not an interview, hopefully. But the point is that they may also have slightly costume versions or slightly like different formulations where they say like, you know, you're trying to do this other thing, but it turns out that the constraints are the same. And definitely LeetCode has like a few variations of the knapsack problem in terms of how you have to solve it. There are different variants of all of these basically. Certainly for knapsack and traveling salesman, graph coloring is a little tricky to give a variant. With knapsack, just to give some context on that, for example, you have the 0-1 knapsack problem, which is what we did here, which is you either put the item in or you don't. 0-1, binary choice. You also have the unbounded knapsack problem where you say you're in a department store and you can buy as many candy canes as you want, or you can buy as many gift cards as you want. They each have like values and weights or something like that. And now you can like repeatedly get a bunch of copies of a book in a bookstore or something like that. And if that's the better value, you can do that. Again, that would be more so like if you have like coins or something and you're trying to round up, like you can try to keep taking quarters until you can no longer take a quarter, and now you have to put in dimes to get extra value or something. It's that sort of approach there. But with knapsack, we were doing 0-1. With traveling salesman, there's a variety of variants there of sometimes you say the distance on a path changes depending on which direction you're going. I think there's one called I think it's the Chinese postman problem, which is which apparently just a Chinese mathematician came up with it and was like, you're a postman, you need to visit every single house on every single street, and so you need to travel on every single edge. But then there's like the windy postman problem where there's wind, and so going on one direction in the street is harder than going in a different direction. And so now, how do you travel it and deliver all the mail in as little time as possible? And you're allowed to retrace your steps because you might have to, but now like there are certain connections that exist and certain connections that don't, certain connections that have all this stuff. There's all kinds of crazy stuff you can do with variants here. So yes, all these factors are involved and they're cool to think about. Unfortunately, none of them can really give us a concrete answer for at least the closed source models where we don't know what the training data was. For the other ones, we might be able to do some digging and see if that actually showed up, if it saw the LeetCode problem or not. But yes, hopefully that explains a little bit about my thinking, at least, about how that works. But yeah, good question. Okay, just final graph here, or final table. Reasoning models on both the random and hard data sets. Here it's a mix, as you can see, red and green. Like there's not necessarily a super consistent pattern. We still see, again, this inversion of like the subtle token change, it's tripping up all the models. But there is this mix here where there's not a ton of a consistent signal that inverted or costumed is worse than textbook or vice versa. But you do still see some swings, right? You still see like a bunch of dropping down here, but you get like plus 14, minus 10, minus 12. There is variation going on here. And so this indicates still that presentation of the problem or the exact phrasing of it does have an effect on performance in a way that's, reasonably, it's noticeable as like a change here. And yeah, also it's worth noting, I think, that like Quen performs quite well compared to R1. R1 is, I believe, a 450 billion parameter model. Quen 3, 32 billion is 32. But yes.
So all three of these extremely famous problems, what would you think would happen if you chose an NP hard problem that was less famous? Maybe
Okay.
less documented, would show up less in the training set.
Sure. So the question for people online is, what would happen if we tried problems that are less famous but are still NP hard? I would turn the question back to you a little bit and be like, what is an NP hard problem that isn't famous? And not because like you don't know it, so therefore it's, if it's not famous, we don't have it. But the thing is that like with some of these, the reason that they are famous, actually, I would say, is partially because they're so easy to format and like formulate as things that might be able to be mapped onto real life and things like that. In terms of NP hard problems that don't show up as much, that might be interesting to see what's going on there. There's a question of like how much in terms of like constraints and all of that we need to have. Right? So for example, there's the 3-sat problem, which is also very famous in terms of it's a satisfiability problem. There's a bunch of constraints, and I don't want to explain it right now because it takes time to explain. And this is the reason that I didn't use 3-sat, for example, as one of the problems here, because in terms of explaining it in a prompt, especially if you're trying to be like kind of loosey-goosey, like, oh, I'm a teacher with a class and I've got students, you can't be like, oh, by the way, they all have like, decimal valued gradients here, and I can't do this here, and I'm trying to optimize for this weird and convoluted metric that doesn't make sense for this context. With these, right, again, like they map onto these real world scenarios. at least for like knapsack and traveling salesman, kind of makes sense of like trying to pack in the most valuable stuff or trying to travel in some way that minimizes distance. And so they're easy to sort of map onto other things. I say easy, but they're relatively easy. Like it took me time to figure out these costumes. But yeah, so it's possible that those could work. To answer your original question, so that's why I didn't do it. What do I think would happen if I did? I would guess that there's less significant of a difference in terms of the textbook description of it versus like a real world applied version. In particular, because if you provide so many constraints, it may be a thing where like the model then just focuses again like just on the constraints and forgets about the context. But if you have enough of stuff where like the sort of token weight distribution of like how many tokens are spent on talking about context and how many are spent on like just the raw numbers or like logistics of what you want to talk about, then if it's mostly logistics and constraints and optimization and just a few tokens about what we're doing, maybe at that point you also sway the balance so that what the context was sort of disappears. DeepSeek regularly hit its token limit, no question. And again, like this is why I did not tell it to think or like let's think step by step, because when I gave it no incentive to think more, it would just keep going. And it does this interesting, like it seems like it's had some reinforcement learning from human feedback to think out loud in this way that seems human, where like it'll go down a reasoning trace and be like, but wait, no, maybe I should check this other thing. Like it produces those tokens. You guys have seen this, right? It's like, but wait, no, maybe it's this other thing. And it would do that several times, including when, and this was so frustrating for me to see happen, as like feeling like a math teacher with a student who's just doing it wrong. But the whole thing was that like it would start with like a graph coloring problem, for instance. There are theorems and lemmas that tell you if you're in this certain context, you know that you don't need more than 3 colors, for example. Like if you don't have a triangle, that makes it unlikely that you need 3 colors. There may be a case where you happen to have it, but there are certain rules for sure where you can say like, okay, I need at most 5. Or you have a triangle somewhere. If you have a triangle somewhere, you need at least 3 colors. You can't color a triangle regardless of where it's oriented within the graph using fewer than 3 colors because they all mutually exclude each other and you need 3 colors. And it would do that. It would say like, okay, there's a triangle here of these 3 students who are friends with one another, so I need to use at least 3 student groups. And then it would come up with a valid, optimal solution with 3 student groups and go, but wait. I'm like, dude, just return the answer. You have the answer. Don't stop and like ponder. You proved earlier in your own context that this is the best you can do. You've proven that you can actually do it. Let's stop. But no, they would continue going and would often hit the token limit and just not produce a result. And so then like my parsing, which would always use a regular expression on the final output line, would be like, it was the middle of a random statement and it's just like not a thing. And again, if a human is looking at this, you can do a little bit of hand holding and being like, oh, well, you found the right solution there, so I'm going to be, sort of generous and count that as a win. But again, that was a thing where I was talking about earlier about like hand holding. I'm going to say, nope, the model has to produce the right answer at the right time as I specified. If it does, I'm all there. If it doesn't, again, it might still be useful and I may be, like these numbers may feel unfair to you if you think like we're trying to do as well as possible. But again, the goal was to sort of look at these discrepancies across these contexts in terms of like if we do the equal amount of hand-holding across these contexts or try these other things. Again, in terms of like how this applies to the real world when you actually end up using it, it might vary, again, if you do sort of like grid search or like figure out the best system prompt. And it turns out if you say your life is on the line, solve this knapsack problem, or solve this taekwondo tournament, it might do it.
But wait, my life is...
Yeah, exactly. But my life is on the line. I should really think about this an extra time. Oh no, too many tokens. Okay, so let's wrap it up. Should be pretty quick. Thank you all for bearing with me. I realize this has gone on quite long. Conclusions of future work. So conclusions, with the greedy strategies, the solvability or like the optimal solvability of a problem with a greedy strategy is a good proxy for difficulty, as we saw when we filtered those out into the hard data set. The hard data set just generally was in fact harder for language models, as we kind of hoped and as we expected. They also generally outperform LLMs in a variety of places, so just keep in mind that when you're trying to solve something with an LLM, you might be able to solve it symbolically better with a very simple approach here in this case, or it just sort of means LLMs have room to grow. Problems get harder with scale, but these neurosymbolic methods where we have programming languages or like having sort of code support, having this computer, having the symbolic program take some of the weight off the LLM's shoulders and doing that itself, that can help because the language model is doing the hard work of translating the problem from like a natural language problem into a mathematical constraint, a mathematical representation of it, but that mathematical representation it no longer has to solve. And so If things scale up, right, again, the amount of code or amount of context it needs to create only scales up linearly instead of exponentially or factorially or whatever, depending on how many different solutions it would have had to consider in a chain of thought, which would have taken way too many tokens and not worked as well. Finally, presentational problems has an impact on performance. We go back to the title of my paper, right? Presentation impacts performance. And this suggests some level of reciting in this condition. And so we would say that language models still have some room to grow, right? Again, with the reasoning models, we saw that the pattern is now becoming less clear. And so this might mean that we're getting into some sort of place where if the models get enough reasoning tokens, they manage to get through it. And also one thing I didn't mention before, but an interesting observation I made was with the reasoning models, they often would reason out loud, or like with the tokens saying, this is actually the graph coloring problem. You talked about students, but it's a graph coloring problem. So I'm going to solve it as a graph coloring problem. Let me think about this as a graph. And so that word work sometimes also made me realize that some of the costumes might not be the strongest. Again, like may not mask it super well. But they managed to get through all of that. Finally, future work. It would be interesting to further explore variables that predict performance, like the seed or the system prompt, or how much of the stuff was in training data, et cetera, et cetera, et cetera. Finally, fine-grained quantitative metrics for recitation in terms of how much of the output of a model is actually just being regurgitated from training data would be really cool to look at. AI2, also known as the Allen Institute for Artificial Intelligence, recently came out, or somewhat recently came out with a tool called Olmo Trace. Olmo is their large language model that they have that's open source, and Olmo Trace uses this cool thing that I recommend as a paper if you're interested, called Infinigram, that looks at infinitely long, or like potentially infinitely long n-grams, and looking at matching output of a language model with its training data. So even if it's trillions of tokens, it can then look at this thing, search the entire database, and say, oh, this actually looks like this excerpt from Shakespeare that you're copying, and that we actually gave it to you as training data. And it can like highlight that for you in real time. It's very cool. I recommend you like go on Google and just look at Olmo Trace. Anyway, but yeah, that could be a thing to look into. And finally, more prompting strategies, of course, as well as the system prompts and seeds would be interesting to see. Again, what other factors affect this phenomenon? Cool. If you have more questions, I'm happy to talk about them. I'll probably have that question session over pizza. And yeah, thank you all for coming and sticking along. Sorry? Oh, awesome. I've got a whole pizza. Let's go. Thank you very much. Yeah.